You are watching one of a series of videos giving an introduction to OrcaFlex. The first 4 of these videos, which we've called the fundamentals, are those that we would regard as prerequisites for looking at any of the other subsequent topics. If you are already familiar with these fundamentals, you may want to pick and choose the subsequent videos you watch based on your area of interest. If you're a complete beginner with OrcaFlex, I would strongly encourage you to watch the full series in order, as this will give you a good basic overview of the program, how to navigate it, and where to access and input data. It goes without saying that the quality of any OrcaFlex analysis is only as good as the quality of the input data, and that, of course, relies on the skill and experience of you, the user. These videos will help you to learn how to use OrcaFlex as one of your analysis tools, and I do hope that you find them educational and maybe even a little bit enjoyable too. In this video, we will learn about line types, as well as taking a closer look at line contents. For some objects in OrcaFlex, the data is split up into 2 separate data forms. For example, with lines, we have the line data form, which we've looked at in a previous video. The line data form contains the data specific to that instance of a line, such as its length and how it is positioned in a model. We then have the line types data form. This contains the data for all the different types of line in a model, including things like their geometry, their structural properties, and their drag and lift data. Line types can be used in multiple lines in a model and are specified on the structure page of the line data form. As well as being accessible from a button at the lower left of the line data form, you can also open the line types data form directly from the model browser. Note that you will only see this in the model browser if you have at least one line in the model. Note too that the data on the line types data form can be viewed individually or with all line types at once. We will stay with the All View mode and look through the various pages of data now. Firstly, we have the Category page, where we have 3 options to choose from: General, Homogeneous Pipe, and Equivalent Line. We'll come back to the General category in a moment. The homogeneous pipe is appropriate for modelling a line constructed from a single homogeneous material, such as a steel pipe. The mass per unit length is derived from the inner and outer diameters and the material density, all input on the geometry and mass page. The stiffness of the line is derived from the Young's modulus, input on the structure page. The homogeneous pipe also allows for inner and outer diameter to vary with arc length. This is done through the use of a variable data item, the availability of which is indicated by the small down arrow button to the right of the data item value. You can select a previously created variable data source here, or create a new one using the variable data item. This is useful for modelling such things as bend stiffeners and stress joints. The equivalent line category is intended for simple modelling of combinations of lines, such as pipe-in-pipe applications. The view mode needs to be set to individual for this category. Overall properties such as geometry, mass, and stiffness are calculated based on the individual line types specified: a carrier line and 1 or more secondary lines. The general category is used for all other applications. Data such as stiffness and mass per unit length are entered directly instead of being calculated from the Young's modulus and material density. This provides more control and is useful for lines with multiple materials such as umbilicals, flexible risers, and hoses. Before we look at the individual pages, it's worth noting that you can look at a properties report for line types. This is accessible from the context menu using the right mouse button or the shortcut Alt and Enter. This tells you, amongst other things, the submerged weight per unit length. If this value is positive, the line will be net heavy. If negative, the line will be net buoyant. As well as the report for line types, we can also view a properties report for the line itself, giving us a useful summary of the actual properties of the line in the model. This is available from the Line Object context menu in the model browser, or by using the context menu on the line data form. As well as a summary, the details page shows us the properties per line section and per segment. This is especially helpful for a profiled homogeneous pipe where properties such as mass and stiffness vary with diameter. As with all properties reports, this can be copied and pasted into Excel or exported directly to an Excel, CSV or TXT file. OK, you can see that we have 3 line types already created in this model, one for each category I've just mentioned. Let's rename them for the sake of clarity as we discuss each page. This can be done by double-clicking the name on any page or highlighting a name and pressing F2. As we discuss the various pages, I will compare the differences between the general and homogeneous line types. The equivalent line type is just a combination of 2 or more other line types, so will not be discussed any further in this video. The first page we'll look at is the geometry and mass page. Here we specify the outer and inner diameters of the line, and with the homogeneous pipe line type, these diameters can vary with arc length using a variable data item. Remember, this is indicated by the small down arrow button to the right of the data item value. There's already one variable data item available, which we will assume is for the outer diameter. We'll go ahead and create a second one for the inner diameter by choosing variable data at the bottom of the list. In the variable data item form, we need to create a new variable data source and then add some data for varying diameters with arc length. As we create a table of data, we can inspect the outcome using the Profile button at the bottom of the form. If the profile is the wrong way round, we can use the Reverse button to avoid having to correct the order of the data in the table. Now that the new variable data has been created, we can select it as the inner diameter value. For the general category, the diameters can only be constant values, and the mass per unit length is specified directly. For the homogeneous pipe, the mass per unit length is greyed out as it is automatically calculated from the geometry and material density, as is the centre of mass. For the general category, the centre of mass can be optionally offset, although this value is only used if torsion is enabled on the line data form. Finally, on this page we have the bulk modulus. The default value of infinity means the line type is treated as being incompressible. For a line that is compressible, we can model buoyancy variation with depth by changing this value. Moving on now to the coatings and linings page, and this is where we can specify any additional coatings and linings for the homogeneous pipe line type only. They are typically used with steel pipes to model the additional mass and displacement of concrete coatings, plastic linings, etc. They contribute mass, weight and displacement and modify the pipe's inner and outer diameters, but they do not contribute at all to the structural properties of the pipe. Multiple layers can be defined by thickness and material density using a variable data source. Again, as with the diameters on the previous page, the availability of a variable data source is indicated by the small down arrow to the right of the data item value. In this case, the variable data source allows us to optionally include multiple layers of specified thicknesses and material densities. The next page is called Limits and allows us to specify whether or not a line can support compression. In line types where bending stiffness is negligible, such as a chain, this option should be checked. In addition, we can specify allowable limits for tension and bend radius. These are for results reporting purposes only and do not impact the calculations. Next we'll look at the structure page, where we specify the stiffnesses of the line. For the general line type, these are input directly, and for the homogeneous pipe, they are derived from the Young's modulus. Note that, because we have a profile line type in this example, the derived stiffnesses are not shown, since they vary with diameter. In this case, the properties report for the line in which the line type is used would present the stiffnesses for each line segment, as can be seen here. For constant homogeneous pipe line type diameters, the derived stiffness data is presented read-only in the line type data form, as we can see if we convert the diameters back to constant values. Also on this page is the option to specify additional bending stiffness. The intention of this is to represent the extra stiffness a line may experience from additional coatings or linings, for example, the concrete coating often applied to steel flow lines. We can specify drag and lift data on the next page. Drag coefficients for the axial direction are a fixed constant value, and for normal directions can be constant, varying with Reynolds number, varying with height above seabed, or varying with both Reynolds number and height above seabed. The lift coefficient, acting normal to the line axis, can be constant, varying with Reynolds number, varying with height above seabed, or varying with both Reynolds number and height above seabed. The structural damping page provides an opportunity to include Rayleigh damping coefficients. For most typical cases analysed by OrcaFlex, structural damping has little or no effect on system performance, and with submerged lines in particular, the structural damping is usually negligible in comparison to the damping due to hydrodynamic drag. We can apply added mass and inertia coefficients to a line type, with the ability to also define entry and exit slam forces, which can be constant or varying with submergence. The friction page relates to seabed friction only, with friction coefficients specified here for the calculation of friction between the line and the seabed. Friction is also implemented for other contact models, but the coefficient data is entered elsewhere, for example on the line contact data form or the friction coefficients data form. OrcaFlex uses a modified Coulomb friction model in its calculations, and information about this can be found in the documentation. The data on the stress page is used for wall tension and stress results calculations. And on the contact page, contact diameters can be specified which are different to the geometry of the line. If the default value of tilde is specified, then the diameter on the geometry and mass page is used for contact purposes. If additional coatings or linings are specified for a line type using the homogeneous pipe category, the contact diameters are updated automatically, as we'll see if we add a coating thickness here. Finally, we have a drawing page, common to many data forms in OrcaFlex, where we can set pen width, style and colour. Included on the line type data form is a wizard to help set up a line type for a number of commonly used structures. In some circumstances, for example where supplier data for an umbilical is not available, the wizard can be useful in providing first estimates for preliminary use, giving us suggestive values for such things as bending stiffness and mass per unit length. However, due to the many variations in properties for things like umbilicals, flexibles, ropes and wires, we would always recommend using supplier data where possible. Having said this, one structure where the data is very well defined is for chains, so I'll add a new line type for a chain and demonstrate this. If we select the chain category on the first page, then go to Next, we simply need to enter data for the bar diameter and link type, and the rest of the data is automatically populated.
Note too that the compression is limited option on the limits page is now checked, since a chain can sustain tension but not compression.
The line types data form also provides access via a button at the bottom to the code checks data form, also available in the model browser. Here you can input data for a variety of codes in order to facilitate compliance of a system with that code. Having looked at the various pages on the line types data form, we will now use this in the creation of a simple vertical free-hanging pipe example. Our line will use the data shown here with the structural properties of a steel pipe. Starting with a blank model, the first thing we need to do is insert a line into the model, since the line type data form is not accessible until we do that. On the line type data form, we will select the homogeneous pipe category, as this is a pipe of a single homogeneous material. The outer and inner diameters are 500 mm and 450 mm respectively. The only other requirement for the line type data form is to specify the appropriate structural properties for steel. Whilst we can't select a material by name, in this instance we know that the Young's modulus for steel is actually the default value of 212 E6 kilopascals, so no further changes are required for modelling this steel pipe. Now that the line type data is ready, we can move to the line data form, where we set the data specific to this instance of the line type, namely its length and end positions. So we'll set the length to 20 meters. Now if I drag one of the line ends towards the other, the line eventually takes up a V shape, which highlights an issue with the line segmentation. The line is 20 meters long, but the default line segment length is 10 meters, so this line now only has 2 segments. Not great for accurately modelling the line response. We'll change the segment length to 1 meter and then move on to positioning the line ends. The line hang-off is specified as 0010, so we'll set this as the fixed position of end A. The bottom end is free, so it doesn't have to be positioned accurately. However, it will generally help the static calculation if we position objects close to where we think they will solve. In this case, with a 20 meter line length, we know that the bottom end will hang in a position of 0, 0 and -10. The only other thing we've been told is the end connection stiffness, which needs to be infinity. As we've learned in previous videos, with a non-zero end connection stiffness, we need to change the end orientation of the fixed end of the line such that its local z-axis follows the end A to end B convention, into the line at end A and out of the line at end B. So let's set the end connection stiffness for end A to infinity, and remember that end B is going to be free. And let's quickly run statics just to see the behaviour before adjusting the line end orientation. And I'm also going to turn on the local axes here. So having run statics, this line is actually hanging vertically upwards rather than vertically down. In order for this case to hang vertically down as intended, the declination of end A should be set to 180 degrees. End B is free, so the same change does not need to be made here. And now, when we run statics, the behaviour should be as expected. Looking at line contents now, here on the contents page, and we have three options when it comes to modelling the contents of a line. The first and default option is uniform, which means that the entire line is assumed to be filled with contents of a uniform density. Obviously, if we use the default density of 0, we assume the line is entirely filled with air. The next option is free flooding. This results in the line being filled with seawater up to the instantaneous water surface. The density below the sea surface will therefore be the density defined on the sea density page of the environment data form, which we can see here. We can see this in practice by selecting free flooding for this free hanging line and then viewing an instantaneous value range graph result for contents density. So we'll run an analysis and then go to the results page, select the line and the range graph result type, and we'll choose the variable contents density and the instantaneous value as the period. As we watch the replay now, the portion of line below the sea surface has a density of 1.025. The value specified on the sea density page of the environment data form, and the portion of line above the sea surface has a density of 0. Because of the passing waves, the transition between 0 and 1.025 is constantly moving, since this is an instantaneous value range graph. The final option for line contents is called slug flow, and this allows for contents with spatial and temporal variations. In other words, it's possible to model a line with slugs of fluid passing through, useful for gas or oil export risers, or the progressive flooding or emptying of a line, useful for things like vessel ballasting. So having reset the model and selected slug flow instead of free flooding, we need to set a non-zero flow velocity, and then create one or more groups. I'll choose a single 20-meter slug length, so the number of slugs is just 1, and this slug will have a density of 1.025 tons per cubic meter. So that will simulate the filling of the line with seawater. What we see now when we run a replay is the progressive filling of the line with seawater, as indicated again by the same instantaneous value range graph for contents density. This contents density change is now dependent on the slug flow properties rather than the passing waves, as it was before. Finally, note that it is possible to visualize slug flow in both the wireframe and shaded graphics views by selecting the Draw Slug Flow option on the drawing page of the line data form. We can see the visualization in this model of a stinger ballasting scenario. That then is an overview of line types, as well as a quick look at line contents. We will look in our next video at shapes and contact.